So as I mentioned before, a constraint is made up of points that represent the piece and a polyline which holds information about what that constraint is doing. So to create this, we have a node called connect adjacent pieces. Go ahead and plug that in after the assemble, right after we packed everything. And we're going to use the centroid of each packed primitive to be the point which represents the piece. So again, if I go in here and we look at these points correlate with the center of each piece. This connection describes how that piece is being held together. And so on here we have a bunch of different settings. We have a max search radius. We have max search points. This max connections, though, is probably the most important one. And this will create a whole web of constraints that allow us to control how this is all connected together. So we end up with something like that. Again, this is just geometry. If we go to our geo spreadsheet, this is our primitive attribute right here. We don't have any primitive attributes. And so we'll come back to this here in a second, but we need to actually add some primitive attributes to this so that in the DOP.NET, we can tell the DOP nodes what to do when it encounters these polylines. For right now, though, let's go ahead and set this up to the second input. Let's go in here and create a constraint network. This is the main thing that you want to use. So go ahead and plug that in. You can do that down here or up here near the object. Doesn't really matter. And then create a glue constraint relationship to start. So we do that, plug that into the constraints. And the key here is that, again, we need to tell these nodes how to pick up the kind of constraint that we're working with. So we have glue right here, and in this data name, this is going to correlate with the constraint name that this constraint network is looking for. So if we hover over this, it says data name, but the attribute that it's looking for is called constraint underscore name. And that's just something that you have to know. Let's go ahead and create a primitive wrangle. Set this up after the connect adjacent pieces. So we go like that. And let's say S for string, which means that the value will be some kind of word, right? S at, and then that means we're creating an attribute. Constraints underscore name is equal to, quotations, let's call this glue with a capital G. And then use a semicolon at the end to finish your statement. Now I realize that some of you guys might have just totally stressed out by the fact that I just threw down a wrangle and then I started doing stuff with Vex, right? And I know a lot of you who come from a 3D background and not necessarily a dev background might be very uncomfortable with typing out some Vex and trying to code things in these little snippets. But one thing that I'll tell you is that if you don't know Vex, you'll need to learn it in order to progress further with destruction. As I mentioned before, destruction is not a beginner topic, and at some point or another, you'll need to manage large data sets. You'll need to manage attributes across thousands or even millions of pieces. And the speed offered by wrangles and the control that you can get is just unparalleled with VOPs. It's not really something you want to do with for loops every single time. And so because of that, if you don't know Vex, check out my Vex Foundations 1 course. Vex is its own study. And so I'm not going to try to teach you Vex as we go here. I'm going to assume that you already know a little bit to get by. But just in case you're not aware of the expectation here, just be aware that you'll need to know Vex moving forward to at least a small degree. All right, so now that we've had that little heart-to-heart chat, let's go to our primitive attribute here. We have constraint name, we now have glue, right? That's the attribute that's on every single piece. So when we go to the constraint network, and the constraint network says, okay, I got a relationship coming in here, right there, and it's looking for this data name. This is where we could say glue. It will pick up that constraint name, and now if we go to our simulation, right here, go to the constraint network and choose the second context geometry, because that's where the constraints are coming in, we could see that these constraints are now present, and if we go forward, they're going to hold together Eugene, like a pro. Now, obviously, if you want to change the strength, that will change the strength of the bonds. So if we set that to, let's say, 100 and we go forward, not enough yet, maybe 10. Eventually, we end up with something like that. Now, there's all kinds of different constraints that you can make. It's not just glue. And also another thing to know about constraints is that it's a little bit complicated in the sense that you can make constraints like I just did right here, or you can make them more manually inside of DOPS. We have all these things called anchor nodes. And an anchor, by the way, if you don't know, is basically just the little points that make up the constraints. So the points that identify the pieces, those are called anchors. And so we have that going on. The old way of working before this RBD packed objects had you making constraints more so in DOPS. And so that's why we see a lot of things related to constraints in here. But just know that with this setup right here, this constraint network and this relationship, this is probably the most straightforward way of going about constraints. And if you can do it this way, then you'll probably save yourself a lot of hassle in figuring out how to set this up. So just go ahead and stick with this for the time being. And in the future, we'll go into other scenarios that might be a little bit different in how you generate this stuff. But just know for now that we have this going on. It's a glue constraint. It's pretty cool. Once a certain amount of force has impacted these constraints, they break, they let the pieces go, and we get something like that. There's one more thing you ought to know about constraints before moving on, and that is this rest length attribute. So let's check this on, middle mouse, and you'll notice that on the primitive, on the polyline, we have this rest length. That's how long each line is. It records the length of that line. Now, why do we need that information? Well, it's not so much of a big deal for something like the glue constraints. But once we have something else, a different kind of constraint, let's say the hard constraint relationship right there, this begins to matter a lot more. Let's go down here to the data name and say glue. We're not working with a glue constraint, but again, that's just the tag, the way to identify those polylines here. So let's just say glue and go to the guide options, turn this down. That's just a viewport preview. And we have our rest length that's set to 1. If we go forward a few frames, what you'll notice is that as the pieces break apart, these constraints try to keep a rest length of 1. So if they get stretched out, they're going to try to go back to the rest length. And so let's say that we turn this up a little bit. Let's say we go to maybe 1.5 or 4, right? Now, the new rest length is 1.4 times the measured length of each one of these constraints. And that's the length that each constraint wants to be at. And so that's why you need to keep track, just depending on the constraints you're using, of the rest length. And that's what that's all doing. So anyway, just in case that was confusing, if you saw this length attribute and you don't know why that's there, now you know. And in the next video, let's move on to something else.